Welcome to another deep dive. Today we're going to be talking about some fascinating materials on quantum mechanics.
Oh, this is exciting.
It is. We got this from, a listener, and get this. High school students in Singapore are using a simulation to learn about superposition.
Wow. A simulation.
A simulation.
That's really amazing. It really speaks to how, these complex topics are becoming accessible thanks to like open educational resources and stuff like that.
Absolutely. So let's break down this simulation a little bit. It's called Bound Eigenstate Superposition, and it was created by Wolfgang Christian. And you can find it on a web page that's part of the Open Source Physics at Singapore project.
Yeah. And
Yeah.
so this simulation, it uses visuals to demonstrate superposition, which is like, a fundamental concept in quantum mechanics. Have you ever heard of that term before? Maybe in like a sci-fi movie or something like that?
Oh, yeah, definitely. Usually involves parallel universes, right?
Yeah. The science behind superposition is a bit different, but it's just as wild. It means that a particle can exist in multiple states simultaneously.
Okay, wait. So not different universes, but one particle being in multiple states at the same time.
Yeah. Think of it like a coin spinning in the air before it lands. It's both heads and tails simultaneously until it lands. And in a similar way, a particle can be in multiple energy levels at once until we measure it, and then it's forced to choose one state.
Okay, that analogy helps. But how do scientists actually observe this? I mean, these particles and states are incredibly tiny, right?
Right, so we can't directly see these superposed states, but we can observe how particles behave when we try to measure them. And it's almost as if the act of observation itself forces the particle to pick just one state.
So before we look, it's a mystery. It's a mix of possibilities, but the moment we observe it, it has to make a choice.
Exactly, and that's one of the most fundamental differences between the quantum world and our classical understanding of physics.
Okay, so how does this simulation help us visualize all of this?
Well, this is where the simulation's visual approach becomes really powerful. It uses what we call energy eigenstates as building blocks, and you can almost think of them like individual musical notes, each representing a specific energy level that a particle can have.
Eigenstates.
Okay, yeah, and just like you can combine different notes to create a melody, you can combine different eigenstates to create more complex descriptions of a particle state.
So we're building up from simple to complex using these eigenstates as our Lego bricks.
Exactly, and a lot of times these eigenstates are explored in what we call position space. So imagine a graph where each point on the graph represents a location, and the height of a curve at that point shows the likelihood of finding the particle there.
Okay, starting to get the picture here. So what kind of complex quantum phenomena can we build with this?
Yeah, so the source material that your listener sent in gives two examples. The first is what's called the infinite square well, and the second is the simple harmonic oscillator.
Vaguely rings a bell from physics class.
Yeah, so the infinite square well is basically like a theoretical box, where a particle is trapped and can only exist at very specific energy levels within that box.
Like a bouncy ball in a container, but on a quantum level.
Exactly. Now, the simple harmonic oscillator is a bit more abstract, but imagine a mass on a spring constantly oscillating back and forth. And in quantum mechanics, we can model this behavior at the atomic level.
And this simulation lets you play with both of these scenarios.
Yes. It shows how combining different eigenstates creates different visual representations of the particle's possible states. It's kind of like a digital sandbox for exploring the possibilities of superposition.
This is already blowing my mind, and we're just getting started. But before we dive deeper into those scenarios, I want to go back to something you mentioned earlier, atomic units.
Right.
What are those, and why are they important in this context?
Great question. So when we're dealing with the quantum world, things get incredibly small. Sizes, energies, timescales, all minuscule. And so atomic units make calculations easier by providing a convenient framework.
So instead of saying a millionth of a billionth of a something, we have a more manageable unit.
Precisely. The source material mentions some mind-boggling conversions. For example, 1 unit of time in atomic units is 2.42 by 10^17 seconds. That's a tiny fraction of a second. And 1 unit of distance is 5.29 × 11 meters, about the size of an atom.
Wow, that's incredibly small. And what about energy?
1 unit of energy in this system is 4.36 and then 18 joules. Again, incredibly tiny amounts of energy we're talking about.
So atomic units basically help us wrap our heads around the infinitesimal world of quantum mechanics. It's like a special measuring stick for this realm.
Exactly. It provides a meaningful way to describe and quantify these phenomena at the atomic and subatomic levels. But While these units are really crucial for the calculations behind the simulation, you don't really need to get too bogged down in the numbers themselves to appreciate the overall concepts.
Okay, good to know. I'm sure our listener is eager to explore this simulation. Where can they find it?
Yeah. So the source material, the web page, has a direct link to the simulation. And it also has links to like scientific papers and tutorials if you really want to delve deeper.
Fantastic. And for our listener, we also encourage you to check out the Open Source Physics at Singapore website. They've got tons of resources available for free.
Yeah, it's a fantastic example of how knowledge is becoming more accessible and empowering really anyone to explore these wonders of science.
Before we move on, I think it would be helpful to just do a quick recap of what we've covered so far. So we've established that superposition is this mind-bending concept where a particle can exist in multiple states at the same time. And it's not just theoretical. It's used to understand how these tiny particles actually behave.
Right. And we also touched upon energy eigenstates and how combining them creates these complex descriptions of those states.
And let's not forget those mind-bogglingly small scales. Atomic units give us a way to grasp the tiny world of atoms and subatomic particles.
Yeah, it's a lot to take in, but we're just starting our journey into this really amazing field.
Now we're going to delve even deeper into the quantum rabbit hole. Buckle up as we explore how superposition works in practice and what it means for our understanding of reality. Okay, so we've established that superposition is like this core concept in quantum mechanics, but how do we actually know these particles exist in multiple states if we can only observe them in one?
Yeah, it's a really good question.
It's like they're choosing a costume the moment we try to like sneak a peek.
Right. So the magic really lies in the way particles behave when we do measure them. It's as if the act of observation itself forces the particle to collapse into a single state out of the many that it could be in.
So before we measure, it's like that spinning corn analogy you gave earlier, heads and tails simultaneously. But the moment we look, it has to commit to one or the other.
Exactly. And that's what makes it so different from our everyday experience where, objects have definite properties whether or not we're looking at them. But in the quantum world, it seems like the observer plays a role in shaping that reality.
That's both unsettling and incredibly cool. So it's not that the particles are tricking us, it's more like they exist in this fuzzy state of possibilities until we force them to choose.
It's a great way to think about it. And this inherent fuzziness is what leads to a lot of the strange phenomena we see in the quantum world.
Like what's like an example of something that highlights this like bizarre behavior?
Okay, so imagine you're throwing a tennis ball at a wall. In the classical world, it just bounces back, right?
Right.
But in the quantum world, there's actually a chance that the ball could tunnel right through the wall.
Wait, what? How is that even remotely possible?
Well, because the ball's position isn't perfectly defined. It actually exists as what we call a wave function, which is like a sort of probability cloud that's spread out over space. And that wave function has a tiny but non-zero chance of extending to the other side of that wall.
So it's like the ball's sort of smeared out and a tiny bit of that smear manages to seep through the wall.
Yeah, that's a good way to visualize it. And it's only possible because of superposition. If the ball had a definite position at all times, like in classical physics, it would always bounce back. Tunneling would be impossible.
Okay, my brain is officially doing somersaults. So this simulation that we've been talking about, bound eigenstate superposition, does it help visualize these wave functions and how they change?
Yeah, that's exactly what it does. By adjusting the different energy levels in the simulation, you can actually see how the overall wave function takes shape. It's kind of like a digital playground for exploring all the possibilities of superposition and its consequences.
That's incredible. It's like we're peeking behind the curtain of reality and seeing the machinery underneath. And this tool is freely available online.
Yes, it's part of that open educational resources movement, which means anyone with an internet connection can access it and start experimenting.
I love that. It's making this complex science, which can sometimes seem so intimidating, accessible to anyone.
Exactly. And projects like Open Source Physics at Singapore are breaking down those barriers and empowering people to explore these wonders of science, no matter like what their background is.
This is all so fascinating, but I think our listener might be wondering, why should I care about this? What's the real world impact of all of this quantum weirdness?
Right. That's the million-dollar question. But the truth is, quantum mechanics is already revolutionizing our world in like countless ways.
Really? Like how? What are some like concrete examples?
Well, think about modern electronics. The transistors that power our smartphones and computers and countless other devices, they all rely on the behavior of electrons, which we can only really understand through this lens of quantum mechanics.
Wow, so every time I send a text or browse the internet, I'm tapping into the power of quantum mechanics.
In a sense, yes, and it goes way beyond that. Quantum computing is on the horizon, which promises to tackle problems that are simply impossible for even the most powerful classical computers. And then there's quantum cryptography, which offers these like ultra-secure communication methods. And we even have quantum sensors that are being developed for applications ranging from medical imaging to like precision navigation.
So this isn't just a theoretical curiosity, it's a field that's shaping the future of technology.
Absolutely.
Yeah.
As we continue to explore these mysteries of the quantum world, who knows what other like incredible applications we'll discover. It's a field that is just brimming with potential.
I'm starting to see why you get so excited about these like nuanced details. It's not just about the science itself, it's about all the possibilities that it unlocks for our world. It's like a whole new frontier waiting to be explored.
Yeah, you've hit the nail on the head. It's about pushing the boundaries of human understanding and unlocking possibilities that we can't even imagine yet.
Okay, so we've covered a lot of ground in this episode, from this like mind-bending concept of superposition to its real-world applications. But there's one big question we haven't tackled yet. If something can be in multiple states simultaneously, what does that say about the nature of reality itself? Buckle up, because we're going to venture into the philosophical implications of quantum mechanics in the next part of our deep dive. Welcome back to our deep dive. We've been exploring this strange world of quantum mechanics, talking about superposition and how particles can exist in multiple states at once.
And we even touched on how this leads to those bizarre phenomena like quantum tunneling.
Yeah, and we saw how these seemingly like abstract concepts actually have very real implications for our world.
Driving all these technological advancements that are shaping our future.
But now we're stepping into even deeper waters, the philosophical implications of superposition. If something can be in multiple states simultaneously, what does that say about the very nature of reality itself?
Well, that's the question that's puzzled physicists and philosophers for decades. And to be honest, there's no single universally accepted answer.
So walk me through some of the different perspectives. How do different people interpret the implications of superposition?
Okay, so one prominent interpretation, it's known as the Copenhagen interpretation. And this one suggests that it's basically meaningless to talk about a particle's state before we measure it. The act of measurement itself forces the particle to collapse into a single definite state.
So until we measure it, reality is undefined. It's like this mix of possibilities, and then our observation is what solidifies the outcome.
That's a pretty simplified way to put it, but it really captures the essence of the Copenhagen interpretation. Now, other interpretations, like the many worlds interpretation, go even further. They suggest that all possible outcomes of a measurement actually occur, each in a separate branching universe.
Hold on, parallel universes. Now we're venturing into science fiction territory.
It might sound like something out of a movie, but it's a serious interpretation of quantum mechanics. It proposes that reality is constantly splitting into all these different branches, each representing a different possible outcome of a quantum event.
So there's a universe out there where I didn't choose to do this deep dive today, a universe where I'm doing something completely different.
Potentially an infinite number of universes,
Yeah.
each with a slightly different version of you and me and everything else. But, you know, it's important to remember this is just one interpretation among many, and it's still debated even within the scientific community.
It's like the more we learn about quantum mechanics, the more we realize how much we don't know about the true nature of reality.
And that's the beauty of it. It pushes us to question our most fundamental assumptions about the world around us and opens up this whole new realm of possibilities.
Speaking of possibilities, it makes me think about that simulation we discussed earlier, bound Eigenstate Superposition. It allows us to actually visualize these complex concepts in a much more tangible way. It's like we're getting a glimpse into this otherwise invisible world.
Absolutely. Tools like that are incredibly valuable because they make these abstract ideas more accessible and spark curiosity.
So where does all this leave us? If reality is potentially this fluid, undefined thing until we observe it, what are the implications for how we understand the universe and even ourselves?
That's the ultimate question, isn't it? It raises all these profound questions about the role of the observer, the nature of consciousness, even free will. Does our act of observation actually shape reality? Or is there some deeper underlying truth that we're only beginning to understand?
It feels like we've gone from physics to philosophy to like existential pondering all in the span of one deep dive.
And that's what makes quantum mechanics so compelling. It's not just a set of equations or theories, it's a window into the deepest mysteries of the universe. And it forces us to confront the biggest questions we can ask about existence itself.
This has been an incredible deep dive, and I have to say I'm walking away with more questions than answers.
Me too.
But that's a good thing, right? It shows just how much there still is to explore and understand.
Quantum mechanics is this constantly evolving field, and the more we learn, the more we realize how much more there is to discover.
So if there's one thing we want our listener to take away from this deep dive, what would it be?
Never stop questioning. Never stop exploring. The universe is full of wonders waiting to be uncovered, and who knows, maybe you listening right now will be the one to make the next breakthrough discovery.
Beautifully said. We want to thank you, our listener, for joining us on this mind-bending adventure. We hope you learned something new, or at least had your curiosity piqued by the strangeness and beauty of the quantum world. Until next time, keep exploring, keep questioning, and keep diving deep.